Length of wall is changing, so 5YW will change. What is your new 5YW?
On 01 to 5.
5YW is 10
1 to 5.
00125. Okay. Now then, everything else will change accordingly. What about your delta IY? Delta IY is dependent on your 5YW, I of wall. So it'll change. So it'll have a new shape function. That will change delta I, right? Because your delta IY is changing, your 5YW is changing.
Yes.
And that means your new S-dot properties will change as well, which is your target displacement is 0.519. Equivalent mass is 72,000 kilograms roughly, and roughly 24.5 for your HE. But theta YF will change as well.
Yes.
Strain does not change, but LB, the length of the beam and the height of the beam has changed. So your theta YF will change. That would imply that your ductility for your frame will be altered also. You have a higher ductility now, and your average is
2.57.
2.57. I'm getting 2.63. Anyways, your ductility increased, right? And that's for the frame. What about the wall ductility? You have a different phi YW. LP will change. The top one doesn't change, the bottom one does. So, but you're taking the minimum of the two. So that's the minimum. So it doesn't change as such, but your mu W will change. So mu W, you have a new mu W of 7.76. Your mu SDOF now, as per this formula, your MW, MOTF will not change because those are geometric functions, not dependent on your, they are global geometric functions. You have a new MSDOF, and that gives you a new TE trial of 3.46. Everybody following so far? Now you got to plug that in here, or your Xi wall and Xi frame. It'll give you slightly different Xi from the other direction. And then you combine that to calculate Xi of your equivalent single degree of freedom system, and you have 11.4% equivalent viscous damping for the system in the other direction, right? In the previous direction, or in the previous problem, our equivalent viscous damping was 10.5 roughly. So we were using the 10.5 line. So now your time period will change. And let's say the time period is 4 seconds, so everything else will change with it. So you have to analyze both directions. You get a problem like that. Any questions? Most of you have a working spreadsheet by now? So up till now, we were doing performance-based design, and one of the method was direct displacement-based design. Now, we did direct displacement-based design for a concrete frame and a concrete dual frame building system, right? Now we will move towards what we call unified performance-based design. It's a little bit different than your direct displacement-based design, but it essentially uses most of its facets to come up with a little bit more optimized design, if you will say that. So unified performance-based design was kind of pioneered by Dr. Satyavrata Chaudhary from NIT Silchar, and he has also written a book on performance-based design, and it gives its history, it gives different styles of performance-based design. It also gives an overview of the direct displacement-based design, unified performance-based design, as well as other design types like capacity-based design and so on. I'm pretty sure the book released earlier this year, or maybe late last year, and I think if you are looking into going more in depth in performance-based design, that is a good book to have in your library, pretty much. It's a really good book, and it's laid out a lot of things in a very easy to understand way. So I don't have it right now, but I can show you a copy of it next time when we meet. So it was developed, as I said, it was developed and championed by Dr. Chaudhary in 2007 in Silchar. And essentially what it entails is that we need not only the design drift, Yeah, point. So not only the design drift, but we are also concerned about the state of the beam or the state of the member that there is. So we are looking at interstory drift, which is theta D. By now we know what it is. And we are also looking at member performance level. Performance level. And that is signified by this theta P over there. So if you remember our equivalent single degree of freedom system that we convert our system into, so you have your effective height, effective mass, then your design drift. The total is theta D, or the displacement at top is delta D, and there is a delta Y component to it, which is signifies your yield. But what Dr. Chaudhary did was he defined this gap between your yield and your displacement as theta P, or as maybe the plastic deformation or the member performance level criteria. So our delta or theta D is a sum of theta YF and theta P, which is associated with the plastic deformation of the member itself. From Priestley, we know what theta YF is, right? For reinforced concrete members, everybody remember this by now? Theta YF. So if we combine these two equations, right? So we'll get theta D minus theta P. We take theta P over that side equals right? So what it allows us to do, if you recall our previous examples of when we were doing direct displacement-based design, I was providing you with the height of the beam. This equation will allow us to determine the height of the beam based on what plastic rotation we are assuming or we are achieving. And how is that? So from that equation, you can take HP to the other side. This will allow us to calculate the height of the beam. That will satisfy both the requirements. One is our drift requirement, right here. And other one is our member deformation target requirement, which is theta P. And since we're talking about beam, we can sometimes also call it as theta PB. So from our previous examples, we know what theta D is, right? It's something defined by us. But how do we find this out? Or who defines this? Yes, but we are trying to find the cross-sectional area, right? Is there something in the definition of performance-based design that can lead you to this? So again, this document that comes in handy, it's free to download, FEMA 356. That has some guidelines about deformation. And it states that for immediate occupancy, so remember, this is your design drift, but this is your performance, a member deformation target at performance level, right? The design drift is always associated with a hazard level, as we talked about, because it's your performance objective. And those hazard levels could be immediate occupancy, can define immediate occupancy, life safety, and collapse prevention. And all three different hazard levels will have some different drift requirements. So our FEMA 356 says for immediate occupancy, you should have 1% transient drift with negligible permanent drift. What does permanent drift means? What does permanent drift means? So after the earthquake, if the building is listing or is drifted, the permanent drift should be less than 1%. For life safety, is 2% drift transient with a 1% permanent residual drift. And for collapse prevention, it's 4%, either transient or residual. That's what FEMA 356 says, but FEMA 356 is not the law. There are other guidelines that you can use. So coming back to our SDOF, right? We got that our design drift is a function of our theta YF plus theta P. And then, again, this theta PB is arising from the plastic rotation of the beam. And that's what our performance target is for the member itself. And as I said yesterday, columns are capacity designed. They're designed to remain elastic. You don't want columns to fail. You want the drift and the failure associated with it to be concentrated in the beams. So this equation here can also be written as this one, where it's a function, it's a ratio of your HB over LB, and it's essentially 0.5 EY over theta D minus theta PB. And now this can be plotted, right? What are the variables that we can plot? We can plot a HB over LB ratio versus, for one grade of steel, what can we plot it with? We can either plot it with theta D minus theta PB or just theta PB. There are a lot of different ways we can plot it, and I'll show you one example. So these are our drift limits as per FEMA 356. Again, and for a grade of steel, we know the EY, right, which is a constant. Maximum allowable plastic rotation or plastic theta PB as per ASC 4130, which which is the code for seismic retrofit of buildings in the US. ASC is American Society of Civil Engineers. They publish guidelines. The ICC adopt those guidelines, and then it becomes code. It is 0.00625 radians. That's the maximum allowable drift, plastic drift in the beam. You don't want to exceed that. Does that make sense? So, for a steel of Fy 500 MPa, and plot your HB over LB ratio. The yield strain would be a constant for one grade of steel, which is 0.0025. Looks like that is our favorite grade of steel for all the problems. And then theta d minus your maximum rotation from ASC 41, which is 0.00625 radians. You have that equation, you have a variable here. You have a variable here. You can plot HB over LB versus design drift. And what it does, it gives you some limits. The limits are 0.14 for life safety as your maximum HB over LB ratio, and 0.13 or 0.125 for collapse prevention as your maximum HB over LB ratio. So we have to be within this realm over here for all our designs. So this chart becomes very important when we try to design for our system, where we need these ratios, the maximum considered ratios for HB over LB to size our beams. Questions? Similarly, if you have a higher grade steel, the ratio increases for life safety and collapse prevention respectively, just because your yield strain is higher. So generally you'll find these in the literature for different grades of steel, but you can also create these in Excel if you want to. For different grade of steel, it'll have a different set of curves. Questions? Okay, so what are the steps that we take to design with UPBD, or Uniform Performance-Based Design? As well as a hazard level, right? Or a number corresponding to that hazard level. So this is your interstory drift that you need to decide upon. And then you also have to decide what your theta PB, or what hazard level is your theta PB corresponding to. For example, which is your member performance level. For an example, this can be if a building is designed to 2% drift and life safety performance level. Then we will use our FEMA 356 guidelines to find out what is the maximum theta PB that we can have in our system. Second step would be to decide a hazard level. And that will define your spectras, your displacement spectra. So for example, it could be EC8, Eurocode 8, medium soil, or type 1 condition. ground type B. And let's say 0.06. These are just examples. We can use different examples. For the Indian code, it would be medium soil, 0.035, 0.35 G, seismic hazard, and whatever the zone it is in. Then decide material properties. FCK, FY, what grade of steel are you using? What grade of concrete are you gonna use? Right? Then, step 4 is here. Just compute this. You know this from your previous thing. Yes.
In the direct design based design, sir, we haven't defined any grade of concrete, sir.
Yes. In the direct displacement based design, you haven't.
You only considering the
Steel.
Steel, sir. Yes, sir. But it's a combination, sir.
Yes, but it is mainly it's a deformation state, and the deformation is governed by the steel. But when you're designing, you'll be using whatever the standard
So, sir,
steel.
actually, it's a transform section, but give you M5 curve is for both, sir. Concrete and steel combined.
Sure.
So we have to consider sir, both. So it's at the end of the day, we are only taking epsilon y, sir. That's why I'm asking that.
Yes, and that's what Priestley defined through empirical results as well as numerical models, is that the steel, grade of the steel and the strain in it defines the deformation state much better than the grade of the concrete.
So then we have to go for iteration then again.
Yes. That's the step we're gonna probably talk about on Friday, is that it is an iterative process. If your concrete does not match up, then it's an iterative process. Generally, you start with a quite high grade of concrete anyways, because everything else is capacity design. So you need to design everything else in a much more elastic way, so you end up using a high grade of concrete. But that's a great question. Now, step 5, which will seem similar, would be to take a shape profile. Which is phi I, and again phi I is hi over h for stories less than or equal to 4, or 4 by 3 hi over h for stories greater than 4. Then also you need to find delta C is the displacement of the critical story, which is given by theta D HSC, and then delta I, as we know, is phi I delta C west. L06. I won't write out the formulas because you know it already. You calculate your S-DOF properties. By now you know the formulas for this. And then you'll have a displacement spectra generated. If you do not have one, generate a displacement spectra. And then we have to look into ductility, right? So your displacement spectra. Eight is then delta y is theta yf times he. What is theta yf? And ductility is delta t over delta y. And once you find ductility, you have to find your equivalent viscous damping, which is make sense? Pretty similar to DDBD. From this and the displacement spectra from step 7, you will find what? Time period. Once you have time period, compute KE. KE is 4. Then your final, or one of the final steps is you have your VB is KE times delta D, and then you divvy it up in terms of your height of the building. All good? So one of the things that you can do with this unified method is very quickly calculate what your dimensions might be to achieve that kind of performance target. And then you'll reiterate or iterate and iterate more once you do your performance checks. But this gives you a quick and dirty way to kind of guesstimate the dimensions. So for example, let's say we have a building plan . So for this building plan, if we say our design drift is, that we consider is 2.8, and our target performance level is life safety, right? Let's find the beam size as per the UPBD method. And we'll say our grade of steel make sense? If our grade of steel is 500 MPa, then our strain in steel is 0.00025. So our theta D is 2.8%, which could be also interpreted as 0.028 radians. Now to use this equation where we can try to find HB over LB ratio, we have theta D, but we also need theta PB. So what information we have to find that out? We have life safety, right? And as per the FEMA guidelines, for life safety, we have some kind of transient drift requirement, and the corresponding guideline in ASC 41 is that for life safety, our theta PB, or the average allowable plastic rotation is 0.02. So the average allowable rotation is 0.02. Okay? So let's first do short direction. What's our length of the beam in short direction? It's 5 meters. And just for simplicity's sake, let's call it LBS because short direction and long direction. So our depth HB would be 0.5 Following so far? 0.5, 0.0025, 5, 2.8. Sorry. And if you whip up your calculators, this would come out to be 0.78 meters. That is your height of the beam that is needed for the length of the beam that is given. However, if you recall that chart, इस पे आ सकता है कि वो PowerPoint आ जाएगा?
नहीं इसमें देख सकते हो मोबाइल में
So while they're figuring that out to show the chart, but so HB is this, right? But we also have a HB over LB requirement. So with this HB, what is our HB over LB ratio? How much is that? 0.156. So, if you look at our chart here for 500 megapascal steel, life safety requirement, our top HB over LB ratio is roughly 0.14, right here. So roughly 0.14 is our, but we are way above that for life safety. So we'll have to reconfigure the beam. So we can use the maximum, so our HB over LB ratio, max is 0.14. So our HB that we'll use is 0.14 times length of the beam times 5, which is 0.7 meters. Make sense? So you went to a smaller cross section. Now, for a similar analysis in the long direction, can you do that? Can you find your HB? Everything else will remain the same. Your LB might change.
B in the longer direction. Point 15625 PBC range mass type. I have to take it 0.14.
So what HB did you get?
It's 0.937.
So 0.937, right? Now you have to find the HB over LB ratio with this,
0.156.
which is 0.156, which again is more than the maximum allowed. The maximum is, as per the chart, is 0.14. So 0.14 times 6 is 0.84 meters. So for long direction, HB is 0.0025 times 6 over 1028 minus 102, which is 9.1936 meters. So HP over LB ratio becomes 936 divided by 6, which is 0.156. Again, this does not work because we are capped at 0.14. So our HP over LB is 0.14. So our LP would be 0.14 times LB, which is 0.84 meters. So just to round it off, you can probably use an HP of either 0.85 or 0.9 meters. And at the same time, you can decide on a width of the beam as well. You can keep the both direction beams constant or different, depending on what you want to do and whether you achieve the B over D ratio as well. So you can use a 0.4 by 0.9 cross section for the long direction. And this comes with experience in terms of your design. And for the short direction, maybe use a 0.3 by 0.7 cross section. Following so far? So what do you think is the difference between this and direct displacement based design? Well, before you answer, is everybody following this? So what is the main difference between UPB and PBD-BD?
Earlier we have
So we can design our beam as per our economical because we already know what is the plastic.
For this one? Okay, so which one do you think is better in terms of, not performance prediction, but in terms of more designer input? Probably. The displacement-based design or direct displacement-based design is using just one performance objective target, which is your displacement. Here you have another added target, so you're satisfying two targets. So you know a little bit more about the design, just not only displacement, but also the plastic rotation of the beam. So you have a little bit more control. What do you think are advantages of one versus the other? In which scenario would direct displacement based design be used versus this one? What if we don't have guidelines for theta PB? We have guidelines for those three hazard levels, but what if we don't have guidelines for something else? Then it's an assumption game. So, any questions so far? Well, if there are no questions, let's take a short break, and then after that, we'll do